Okay, so for today, we are going to talk about strain. Strain is a little bit different than stress, but you're going to use a lot of the same thought patterns here. So let's go into it. So the first kind of strain is called direct strain. Direct strain is going to be perpendicular to the face, whichever face is you're dealing with here at least. So once again, the fancy way to say perpendicular is normal, because we're talking about three-dimensional objects, so perpendicular is not really the word that they like to use. So how strain is measured is if you have a box, we'll say, and you're going to pull on the box, what's going to happen is the box is going to stretch just a little bit. All right, so it's going to get just a little bit longer. Now, how much longer it gets is going to be causing strain onto the box. All right, so strain is going to be measured by having the change in length divided by the original length. Okay, so here is going to be your original length. It's that distance there. And this guy right here is going to be the change in length, so delta L. All right, the symbol for strain is going to be this guy. It is an epsilon. All right, it's just another Greek letter, but that's the symbol that they chose for it to stand for. Now, for units for this puppy, this is length, so you can measure it in any unit of length that you like. I'll go with meters because metric system is fun for everyone. This guy is also a length. It is in meters. That means that this strain here, is going to be unitless. So there is no label for there. Now, something else that we know about this is it's going to be small. The reason why it's going to be small is most things cannot stretch very much from strain. They'll just break. You know, if you've ever tried to stretch a piece of metal, it's not gonna do that. It'll just get ripped apart under the forces. And we're going to talk about how it relates to stress tomorrow, but just strain for today. So this is going to be small. Typically, you're going to see a lot of decimal places. What they're going to use a lot of is they're going to use the micro units for this. So you'll see something like, I don't know, 28 micro. Now, since there's no unit for this kind of stuff, they just put the Greek letter. So this would be a measurement of strain. Now, what this actually is going to equal, if you wrote it out in longhand, is it's times 10 to the minus 6. So 0.1, 2, 3, 4, 5, and then there's the other number. Oops, hold on. Sorry, miscounted. 0.123428, right? So this is where the 6 would have been. All right, so this is how much longer it gets per meter, per denominator, right? This would be the numerator divided by 1. Nice. All right, let's look at an example of this. So here we are, a metal wire is that much in diameter, that long, a force is applied, and it stretches by 3 millimeters. So does this feel familiar at all? Anyways, so you have a wire, here's your wire. It was 2 meters long, and it is extended, well, it stretches by 0.3 millimeters. This time we don't care about the diameter because we only care about stuff that's going in the normal direction here. It's only got normal strain, and we don't care about the force. We'll put them together tomorrow. So what we're looking at here is to calculate the strain. We're looking at that, it's going to be delta L over L. So looking at this, we have one of them in meters, one of them in millimeters. Which one do we have to use? Well, it doesn't matter. We just have to make them the same. If I were you and I was doing it, which I am doing it, I'm going to change them both to millimeters. Only because then I get less decimals here, less working decimals. So my delta L is going to be the 0.3 millimeters, so 0.3. And then my bottom is going to be 2 meters. So I have to change that into millimeters. Remember, milli, there's 1,000, right? Like millennium. So this is going to be 2,000 millimeters. And that's what's going to go in the denominator here. So we're going to have 0.3 divided by 2,000. We're going to get 0.00015. Okay, that's good, but let's represent it in a more practical way. This is the same as 150 microstrains. Anyways, so 1, 2, 3, 4, 5, 6, right? So you can always count them out if you're not sure. Hey, and that's how you do that one. Let's try one more. A rod is ½ meter long and that much in diameter. It's stretched by 0.06 millimeters by a force of 3 kilonewtons. Calculate the strain. So we're looking for strain. See if you can set it up. We'll give you a head start. Oh, it took you that long? All right. Well, let's see if I can catch up to you. So this guy, your sigma, is going to equal delta L divided by L, just like before. So your delta L is how much it got stretched. So that's going to be 0.06. All right, we're going to divide that by our other number. How long it is has to be in millimeters to match. So ½ a meter is going to be 500 because 1 meter is 1,000. So all you got to do is divide those numbers there, and you're going to get 120 micro. And that's that. So are we feeling okay about that? Wonderful. There's one more kind of strain, surprise, surprise, and that is shear strain. Now, I know what you're thinking, but no, it's not that. It's shear with an A because it's going perpendicular just like before. So this is opposite directions, right? Sorry. Opposite direction. So if you have a box right here, you have one force that's pushing it this way, one force that's pushing it this way. It's going to deform slightly. It's going to turn into a parallelogram type shape. All right, like a book, right? When you're sliding a book on the table, it'll do something like this. Now, how we measure it, right? It's going to be the same general formula. But what we're going to do here is this amount right here. Let's see. This distance here, this is going to be your change in L. So there's your delta L. And your original L is going to be this distance here. So it's perpendicular to each other, all right? So the delta L and the L are perpendicular. All right. Now gamma, as it turns out, some people might not like this, turns out to be this angle that's formed. Now, you're okay with that now, but the formula is this guy here. It's going to be just like before, delta L over L. Now I know what you're saying. That's a slope. This guy here is a slope. How can it be an angle? Well, this only works because this is a very small angle. All right? It's gonna be a small angle because you can't bend this stuff very much because it'll just break. Now, since it's a small angle, that means that sine of x is basically equal to x. Right? This is that infamous trig identity which only engineers and physicists like to use. So if you're not 100% with that, don't worry about it. So just keep in mind that the gamma is related to the angle, but it works the same way as the other ones. So you have a delta L over L. They're perpendicular to each other this time. They're going to be at a 90-degree angle. All right. So let's do one together. So we have a beam of steel is 3 by 3 square and 0.5 meters long. It's deformed so that the areas are separated by 0.6. All right, so what we've got here is we've got a square that's 3 by 3 centimeters. I guess we should put that there. Okay, normally it would be straight, but it's bent. Well, it's, from the force. Just a little bit. Okay, how much is it bent? Let's pretend this were going straight into there. All right, so this delta L is going to be 0.6 millimeters. 0.6 millimeters. Nice. So our 0.5 is going to be right there. That's in meters. Now we're figuring out the shear stress here. So shear strain, sorry. So we're going to use a gamma. Gamma is equal to delta L over L. Our delta L is easy. That's going to be 0.6. What's our L going to equal? Have you figured it out? Well, remember your L is perpendicular. So this guy is going there. So your L is going to be this distance here. Beautiful straight line drawn. So we're going to divide by not 0.5, but 500. Because you got to convert it to millimeters to match. All right, once we divide those numbers, we is going to get an answer, and that answer is 120. Nice. So that's that one. Let's see if you can do one now. You got a lead pipe able to withstand a deformation of that many millimeters while maintaining below this strain. What's the smallest length of pipe you can use? All right, let's give you a try. See if you can pause the video and figure it out. So here's your pipe. Wonderful. So it's going to be deformed by 1.5 millimeters. And here's the L. I don't know how long it is yet. Now, remember, if it were a short pipe, it's going to have more stress, right? Because you have delta L over L. A short pipe has a smaller denominator, so it's going to have a bigger fraction. This is why we need a longer pipe. So what's the smallest pipe we can use? If we had a huge 10-mile pipe, this would be nothing. There'd be basically zero stress. But what's the smallest pipe we can get away with? That's what we want to know. So we know what this is. We know what the gamma is. It's going to be 230, but it's not just 230. You're going to have to either put in a times 10 to the minus 6, or you're going to have to move the decimal point. Well, tell you what, I'm going to do the times 10 to the minus 6 at least, but that's the same thing. Remember, if you don't have a calculator, is 0.00230. after the decimal point. So these two numbers are the same, but it doesn't matter which one as long as you know how to type it in your calculator. And that's going to equal delta L. We know what delta L is, 1.5 divided by L. So we have to do some cross multiplying action here. And we are going to get L is equal to 6521. That's a big number, but remember, because that's in millimeters, because it's a length this time. Well, let's change it to something more reasonable, 6.5 meters. Okay, hey, that was strain. Hopefully you had fun. We'll see you next time.